Okay, this video will be about the first video on intermolecular forces, and I'm hoping that you can follow along and take some notes as we go here with this, and maybe pause the video here and there. All right, now, so the other day I wanted you to do an assignment where you had to identify the types of intermolecular forces, and you used this flow chart right here. Now, this flow chart is for compounds that are molecular compounds, but there's a little bit more to it than that. So I'm going to have you refer to, I think it's on page 85, 86 in your book, and it looks like this right here. And so I have some notes right here. And so what I'm going to do is I'm going to break all these down and talk about them. And then the next video is going to go over some examples, and the second video will basically go over the back of this worksheet. So the first video will be going over the front of this, the different types. Okay, now there are different types of intermolecular forces. And so I'm going to start with this right here. This is ion dipole and ionic bonding. Okay, we'll go through that first, and then we'll go through some of these other types. So, all right, so I'm just going to go to a slide and draw a few pictures, and I'm actually going to start with an ionic bond. So here we go here. I'm going to go to there. So let me get a new page here. All right, so the first thing is ionic bonding. Okay, so an ionic bond, you might not think of that as an intermolecular force. Okay, so, but basically an ionic bond is a bond between like a positive ion, so we have like a sodium ion and a chloride ion. All right, and so there's a force of attraction between two particles, and an intermolecular force, an IMF, inter means between. So when we talk about IMFs, they are forces between molecules. So they're forces between molecules, or ions with ionic compounds, or there can be forces between ions and molecules. So those are the kind of the types of IMFs that we're going to talk about. We'll start first with an ionic bond. It's the force of attraction between ions. Okay? And so that ionic bond can be somewhat, it's kind of a gray area, but it can be classified as an intermolecular force. Now it's the strongest type of IMF. Okay? Now, a second type we're going to do is between an ion and a molecule. So let's say we have like let me just write this here. So we have and it's called an ion dipole intermolecular force. Okay, now an ion, let's just take like the sodium ion, Na positive, okay? So it has a positive charge to it. Now a dipole is a polar molecule. All right, so if you have a polar molecule, such as water, all right, so let me just draw water here. So if you know water has positive end and it has a negative end. So the oxygen is negative, the hydrogen end of the water molecule, this end of it, is positive. So if we had a positive ion, which end of a water molecule would be attracted to that? Well, it would be the negative end. So this water molecule would be attracted. So here comes the water molecule, and it's going to have the negative end is going to be attracted there, and there'll be a force of attraction right here, and that force of attraction is an ion. Okay, there's our ion dipole, a polar molecule. When they're attracted, the force between them, that's called an ion dipole intermolecular force between an ion and a dipole. Okay? All right, now let's go on to the next ones. Okay, so these next ones refer to covalently bonded substances. If you're following along with your notes here, I'm basically going to go down this list right here. All right, but I'm going to refer back to this right here. Okay, so the first thing is when you're dealing with intermolecular or molecular compounds, you want to see if the molecule is polar or not, okay? And so you can kind of follow this flow chart right here. And so it's either polar or nonpolar, okay? And so I'm going to go back to the sheet that I drew out. And so I'm doing these right here. So if you have a covalently bonded substance, that's like a nonmetal to a nonmetal, okay? It can either be polar covalent or nonpolar covalent, all right? Now, if it's polar covalent, it has some sort of dipole-dipole interaction. Now, dipole-dipole interactions can be broken down into a stronger version of a dipole-dipole, which is called hydrogen bonding, or it can be just a regular old dipole-dipole with no hydrogen bonding. Okay, and I'll explain that in a minute. If it's nonpolar, all right, then it only has what are called London dispersion forces. And I'm going to go through those also in this video. But here's the thing, this is super important. Everything has London dispersion forces because London dispersion forces are based on electrons, and everything has electrons. Okay, so even ion dipoles have London dispersion forces. Even ionic bonds have London dispersion forces. Okay, basically if something has more electrons, it has more London dispersion forces, which means if something has more electrons, it's attracted to itself more than something with fewer electrons, as long as that's the only force. And we'll talk about that in a minute here. All right, so let's go up and let's start with some of this stuff here. All right, so, okay, so if you have something like let me change that. I don't like that color. Let's go to black here. All right. So let's say we have hydrogen H2. Okay, so hydrogen is bonded to a hydrogen. It makes a molecule like that. Now, let's say another hydrogen came along. And you would have to look at hydrogen and say, okay, is this a polar molecule? And the answer would be no, it's not polar. Therefore, the only force of attraction between these H2s, there would be an intermolecular force, however, it's very weak, and that would be London dispersion forces. That's the only force between them. Now, let's compare that to like HCl. So we have HCl, and let's say here's a molecule of HCl, and here's another molecule of HCl. Remember, intermolecular forces are between molecules. Okay, so what type of force would that be in between there? So the first thing that you'd have to say, well, is HCl polar? And the answer is yes, it is polar. All right, now because it's polar, all right, we have to think about, all right, can it hydrogen bond? And in order to hydrogen bond, you have to have a hydrogen bonded to an F, O, or N. And is there a hydrogen bonded to an F, O, or N? And the answer is no. Therefore, this force between these two is only called a dipole-dipole interaction. Okay? No hydrogen bonding. All right? Now let's compare another one here. So let's say we had HF, and we know HF is a polar molecule. And let's say we had another HF here. All right. Now HF is polar, so yes, it is polar. And so we got to think about, okay, well, what's the attraction between these molecules? So you would look and say, okay, is there, we know it's some special type. It could be a dipole-dipole, or it could be a special type of a especially strong dipole-dipole, and it's a force of attraction between molecules. And so we have to say, is there a hydrogen bonded to an F, O, or N? And the answer is yes. Okay, the reason that it's these three atoms here is because they are the most electronegative atoms. And basically what they do is they pull the electrons so far close to them, it makes kind of like an extreme dipole, which makes this attraction stronger than in normal atoms. So, because there is a hydrogen bonded to an F, O, or N, we end up getting what's called, this would be what's called a hydrogen bond. Right here, it's the force though between molecules, not inside of a molecule. That's called a covalent bond. Okay, a hydrogen bond is between molecules. All right, now that's it with that part. Now we got to go through London dispersion forces. So anyway, new page. All right, London dispersion forces. Okay, everything has London dispersion forces. And so the London dispersion forces are based on number of electrons. Okay, more electrons equals greater London dispersion forces. All right, now let me just explain that. So let's say we have a hydrogen, and here's a hydrogen bonded to another hydrogen. All right, now they share 2 electrons. Okay, and here's another hydrogen bonded to another hydrogen. Okay, now the electrons are moving around, and so I'm going to draw the electrons in red. Let's say they move around, and so anyway, the electrons move around, so instead of being evenly distributed, let's say they're a little bit closer. So disregard the black ones. Let's say the electrons have moved over to this side of this molecule. That makes this side slightly negative and this side of the molecule slightly positive. All right? Now, this slightly positive end of this molecule can draw the electrons from this hydrogen, okay? And that's called inducing a dipole. It can pull the electrons over here, and it can make this side slightly negative, okay? And then this side will be slightly positive. And so then there's going to be a force of attraction, however it's very weak, okay, between the 2 hydrogen atoms, and it's called a London dispersion force. Everything has London dispersion forces. Now, let's compare that to bromine and bromine. Okay, so a bromine and a bromine, okay, bromine has, what's the number? I don't have a periodic table, but it's something like 35. So bromine has something like 35 electrons. So just think of all these electrons scattered all about here. And I didn't draw exactly 35, but anyway, here's another bromine to bromine. And just think about all the electrons in bromine, okay? They're all scattered all over the place, okay? Well, bromine has more electrons than hydrogen. And because it has more electrons, bromine, and here's a term for you, things with more electrons are said to be more polarizable, if I spelled that right. Okay, they're more polarizable. This is a very important term. More electrons equals more polarizable. What that means is more electrons can be distributed on one side than the other. So let's pretend all these electrons move over here. That's going to give this side a very strong negative charge and make this side very strongly positive. With more electrons, it can get more charged on one side than the other. It becomes more polarizable. Okay? And so that's what can happen over here also. Then this positive would pull these electrons more to this side, and it makes what's called a stronger dipole. These London dispersion forces can turn a thing that doesn't have a dipole into a dipole, kind of, by polarizing them, making them more positive and negative on one end or the other. And so there's a stronger attraction. That's why the attraction is stronger down here in Br2 than H2 up here. Okay? So the London dispersion forces, they're more electrons, greater LDS. That's a very important thing to remember. It's because they become more polarizable. You'll need to use that word when explaining some of your explanations that we're going to practice later here. But more polarizable. I'm clicking all the wrong buttons here. All right, everything has London dispersion forces. It's more polarizable. Now, there's one last thing I want to show you right here. Okay, so, and this is not on your note sheet, so make sure you write this down. Okay, so there is something called this right here. It's called, like you can have what's called a dipole, induced dipole. So you can have what's called a dipole, induced dipole. This is what happens. Okay, so let's say we have a dipole, like let's say we have HF. And so like let's say we have a molecule right here of HF. HF, this side of it's going to be negative, this side's going to be positive because it's a polar molecule. You could draw this to show that if you wanted. But anyway, this side's going to be negative. Now, let's say we had a molecule of H2 over here. Now, H2, okay, has its electrons here. It's a non-polar molecule. There's not really a positive or negative end here. But remember, hydrogen has these 2 electrons, and they can move around. Now, when this molecule has a negative end, it's going to attract or repel the electrons in hydrogen, and it's going to push them to the other side. And so hydrogen's electrons with H2 are going to be pushed over to this side because they're going to repel. Now, that's going to induce, that means cause, okay? It's going to cause a dipole in this H2. And so this end of H2 will become slightly positive, this end will be slightly negative, and there'll be a force of attraction here. Now this type of attraction is called a dipole, induced dipole attraction. A dipole, induced dipole attraction. Okay? Now that happens when you have an attraction between a polar molecule and a nonpolar molecule. Now that one is not on your note sheet, but that's something important to know. Okay, that's it with this video. We're going to the next video is actually practicing some things, so it'll be an important one to watch.